Welcome back to AI.Code.Cast. We love diving deep into these fascinating algorithms, and today we're going to be tackling the majority element problem.
Ooh, that's a fun one.
Yeah, imagine like you're given this massive data set of numbers, right?
Yeah.
And you have to find the one that appears more than half the time.
It sounds,
Simple at first.
yeah, deceptively simple.
It could get
Real tricky.
real tricky.
Yeah.
Yeah, and you know what's really cool about this is it's not just like some theoretical thing. It actually has applications, in data analysis and voting systems.
Absolutely.
Even image processing.
Oh, yeah. Think about like finding the dominant color.
Yeah.
In
Yeah.
a picture. That's a majority element problem.
So, okay, let's unpack this a little bit more.
Okay.
We've got this array of numbers, right? Could be thousands, millions, billions even.
Huge.
And we need to find that one superstar number, right?
The one that's
That holds the majority.
more than half.
More than half, yeah.
Yeah.
So when you come across a problem like this, what's like the first approach that pops into your mind?
The most intuitive one for most people is brute force.
Brute force.
You just like go through each element in the array one by one. You count how many times it appears. If you find a count that's more than half the size of the array, well, boom, you found the majority element.
That does seem
Easy peasy.
pretty straightforward.
In concept.
Yeah, but I have a feeling
It's not the best.
it might not be the most efficient,
Especially when you've got
especially with these massive data
these
sets.
giant data sets. Yeah.
Yeah, it's kind of like trying to find, a specific grain of sand on a beach by like
Looking at every single one.
examining each one individually.
Yeah.
Yeah.
Not a good use of your time. So
Yeah.
brute force.
Brute force is out if we're
Wow.
trying to be efficient.
Yeah, you got to think about efficiency when you're dealing with algorithms, and we often talk about that using what we call big O notation.
Big O notation.
It's a way to kind of express how the performance of an algorithm changes as the input size grows.
Okay.
And brute force, in this case, has a time complexity of O of n squared.
O of n squared. So that
School
means
friends.
that as the array size increases,
The time it takes.
the time
the-
it explodes, it grows exponentially.
Exponentially, yeah.
So if our array size doubles,
The time to find a majority element
it could potentially quadruple.
could quadruple. Yeah.
Ouch.
Yeah, not good.
That doesn't sound
Not scalable.
scalable at all.
Imagine you're trying to analyze voting data for like a national election.
Right.
Using brute force, oh, it'd take forever.
It would take forever.
Yeah.
Not going to happen.
So brute force is out.
Out the window.
What other tools do we have in our, algorithmic toolbox
Well, let's...
to solve this problem more efficiently?
One thing that comes to mind is using a data structure called a hash map.
A hash map.
Have you heard of those?
I have heard of a hash map. Yeah, it's like a super efficient lookup table. So instead of counting each number one by one,
Right.
you use the hash map to store each distinct number as a key,
Okay.
and then its count as a value.
So as we're going through our array,
Yep.
we're checking if a number
So if it's already in the hash map,
is already in our hash map.
if it is,
If it is, we increment the count.
you got it.
If not, we add it to the hash map with a count of 1.
Exactly.
So it's kind of like we
It's
have
like a designated spot.
a designated spot for each number
Yeah.
to keep track of its,
Popularity.
popularity.
How popular is this number?
Yeah, exactly.
Yeah, and by using a hash map, we can bring that time complexity way down
Okay.
to O of n,
O of n.
which is a linear relationship between execution time and array size.
So if our array size doubles,
The execution time roughly doubles.
roughly does it.
Much more manageable.
It's
Way better than brute force.
way more efficient.
Yeah. Yeah.
But are there any trade-offs?
You're catching on.
There's
There's no such thing as a free lunch.
no such thing as a free lunch in the world of algorithms.
Usually not.
So what are we trading off here?
Well, the trade-off here is space complexity.
Space complexity.
Hash maps are great for time efficiency, but they need memory.
You need memory to
Store
store
all those key value pairs.
all those key value pairs, right? So we're saving time, but
It might end up
we might end up using
using more memory.
more memory, especially if our data set has
Especially if you got lots of unique numbers.
lots of unique numbers.
In the worst case scenario,
Okay.
where every element in the array is unique,
Yeah.
the space complexity of our hash map solution would be O of n,
O of n.
meaning the memory usage grows linearly with the size of the array.
This is getting interesting.
Spicy.
got two very different approaches now.
Two different tools.
With their own advantages and disadvantages.
Each one has its pros and cons.
Yeah, and it's really making me realize that
it's all about, choosing the right tool.
Choosing the right algorithm for the job.
For that job, yeah.
Yeah, and there's no one-size-fits-all solution.
Nope.
It's awesome.
So we've seen brute force, we've seen hash maps, but did you know that we can actually use sorting?
Sorting?
To help us find the majority element?
Now that you mention it, I vaguely recall.
You're digging deep into those research materials.
Digging deep into the research materials and seeing something about that. But how does sorting?
It seems a little counterintuitive.
Yeah, it feels like we're shifting gears a bit here.
A little bit, but think about it this way. If you sort the array in ascending order, the majority element, because it occurs more than half the time, has to occupy a specific position in that sorted array.
Okay, let me try and visualize this.
Visualize it.
If we line up all the numbers from smallest to largest, the majority element would need to be
just going to be clustered.
Clustered around the middle.
Around the middle.
To make up more than half the array.
To be the majority.
Okay, I'm starting to see it.
So by sorting the array, we guarantee that the majority element is going to be right there in the middle.
Right at the middle index.
At the middle index.
So we just sort the array, we grab the element at the middle, and boom, we found our majority element.
There it is.
That's
pretty slick, huh?
That's pretty elegant.
Yeah.
It feels like a shortcut compared to
a little shortcut.
All that counting.
Yeah, it is, but of course.
Yeah, there's always a
trade-off.
What's the trade-off?
Sorting itself has a time complexity of O of n log.
O of n log n.
Which is a bit slower than that O of n we got with the hash map.
So we're trading
a little bit of speed.
A bit of speed for...
But we're getting...
It's simpler.
Potentially simpler.
And potentially more intuitive approach.
More intuitive.
Okay.
And there's another potential advantage here.
Oh.
We can often sort the array in place.
In place?
Meaning we don't need to allocate a bunch of extra memory proportional to the size of the array.
So in terms of space complexity, sorting could be more efficient.
Could be more efficient.
Than using a hash map.
If memory usage is a big concern.
If memory usage is a major concern.
Yeah.
This is cool, I'm realizing.
You're seeing the big picture now.
That there's so many different ways.
So many different ways to approach this, and they all have these trade-offs.
It's all about trade-offs.
It's fantastic.
And you know what? We've only just scratched the surface.
We've only just scratched the surface.
Of the majority element algorithms out there.
Wow.
There's even more clever and efficient approaches.
I'm already feeling like my algorithmic muscles are getting
workout.
A workout.
Yeah.
But
before we go too deep.
Before we jump into those more complex solutions, maybe we can just take a step back for a second and address some of the potential pitfalls or common questions.
The gotchas.
The gotchas, it might come up when someone is tackling this problem. Make sure we have a good understanding.
Yeah, make sure we have a solid understanding.
Of the problem.
Of the problem before we dive into those more intricate...
It's really crazy solutions.
Solutions, exactly.
Yeah.
Like, for instance, what happens if the array doesn't actually contain a majority element?
Good question.
Will our algorithms still work correctly?
Well...
Or are they going to...
some of them...
Go haywire.
Make assumptions.
Yeah.
They assume that a majority element exists.
Okay.
If it doesn't, they might not give you the right answer.
They might not give us the right answer.
Or they could even lead to errors.
So before we even start implementing...
Yeah, got to think about that first.
Any of these solutions, we need to carefully consider whether a majority element is guaranteed to exist.
Is it guaranteed?
Or if we need to build in checks.
Do we need to add a check?
To handle the case?
What if there isn't one?
Where it doesn't.
Yeah.
So it's all about understanding...
I understand the limitations.
The assumptions.
And
limitations.
Of each algorithm.
And making sure that they align.
It's got to make sure it's the right tool for the job.
With the specific problem that we're trying to solve.
Exactly.
Yeah.
What else could go wrong?
I'm making a note of that.
What other tricky scenarios?
Yeah. What other potential pitfalls or tricky scenarios should we be aware of?
Well, you got to watch out for those edge cases.
Edge cases?
Like what happens if the array is empty?
Okay.
Or what if all the elements are the same?
Yeah.
This seems simple.
Those seem like really trivial.
But they can trip you up.
They can trip you up if you're not careful.
Especially if you're not paying attention.
It's like those, seemingly simple math problems.
Oh, yeah.
That turn out to be way more complex
than you initially
thought.
So, I always get it.
So we need to carefully consider all the possible input scenarios.
All the possibilities.
Including those edge cases.
Especially the edge cases.
And make sure that our algorithm
can handle it.
Can handle them gracefully.
Gracefully.
Yeah. Okay. You ready for the next level?
I think I'm ready to tackle some of the more sophisticated, the really fun ones.
The really fun ones to the majority element problem.
So how about we try to work our way towards a more efficient solution together?
Okay.
I'll give you some hints.
Okay.
And we'll see if we can come up with the most optimized approach.
Ooh, I like the sound of that.
Little algorithmic treasure hunt.
It's like an algorithmic treasure hunt. Let's do it.
Let's go. Okay, so you ready for this treasure hunt?
Yeah, I'm ready for some hints.
All right, so here's your first clue. What if, instead of focusing on counting how many times each element appears, we try to keep track of a potential leader as we move through the array?
A leader. So we'd be picking a candidate for the majority element.
Yeah, like a front runner.
And somehow tracking its lead.
Its advantage.
Over the other element.
Exactly. Right. So now imagine that each time we encounter an element that matches our current leader, we increase its lead. And if we see an element that's different, we decrease the lead.
Okay, I'm kind of seeing where you're going with this.
Yeah.
It's like a popularity contest.
It is.
Our leader gets points for each supporter and loses points for each opponent.
Yeah, it's like a voting system.
But what happens if the lead drops to 0?
Good question.
Does our leader get disqualified?
You're exactly right. If the leader's lead shrinks to 0, that means we've encountered an equal number of supporters and opponents.
Right.
Essentially, our leader has lost their mandate.
So we need to elect a new leader.
Gotta have a new front runner.
Do we just pick the next element in the array as our new leader and reset the lead count?
Reset the count to 1.
Back to 1.
And then keep going.
And then we continue our journey through the array.
Keep track of the new leader.
Tracking the lead of our new leader. Okay, this is starting to sound like a very dynamic process.
Very dynamic.
Leaders rising and falling as we go through. But how do we know that this leader-following approach will actually lead us to the true majority element?
So that's the really clever part of this algorithm. The key insight here is that if a true majority element exists, it will always outlast any other element in this lead game. Because if a number appears more than half the time, it's inevitably going to accumulate a positive lead. That cannot be completely wiped out, even when it encounters a sequence of different elements.
I see. It's like it has a head start.
A marathon?
In a marathon.
Where the majority element has a head start.
And it can't be overtaken.
And it can't be overtaken even if it slows down occasionally.
Even if it hits a rough patch.
That's pretty ingenious.
It's a pretty neat algorithm. It's called the Boyer-Moore voting algorithm.
Boyer-Moore voting algorithm.
Have you heard of that one?
I'm adding that to my algorithmic vocabulary.
It's a good one. So let me recap. We pick an initial leader. We track its lead as we iterate through the array. We change leaders if the lead drops to 0 and the final leader standing.
Is our winner?
Is our majority element. Did I miss anything?
You got it. And here's the best part. This algorithm has a time complexity of O of n.
O of n, so it only needs to traverse the array once.
One pass through the array.
Wow.
And even more impressively, it has a space complexity of O of 1.
O of 1 meaning?
It uses a constant amount of memory.
A constant amount of memory.
No matter how big the array gets.
Regardless of the array size.
So we've gone from brute force?
Yeah, we've gone from this potentially time-consuming,
whole-consuming,
and memory-intensive brute force approach
to this super streamlined solution.
To this very elegant solution.
And that's the power of algorithms.
That's amazing.
Understanding those trade-offs, finding the right tool for the job.
This has been really eye-opening. I'm starting to appreciate the art and science behind.
Yeah, it's a beautiful thought.
Algorithm design.
It's like puzzle solving, but with real-world implications.
It really is.
And you know what? This is just the beginning.
This is just the tip of the iceberg.
There's a whole world out there.
There's a whole world of algorithms out there.
It's just waiting to be explored.
I'm feeling very inspired. To dive deeper into this world.
So before we wrap up...
before we wrap up...
Any thoughts for our listeners?
Yeah, any parting thoughts or advice?
Especially those who might be feeling a little overwhelmed.
Yeah, overwhelmed by all these different algorithms.
Don't get too hung up on memorizing specific algorithms.
Right.
The real key is understanding the underlying principles.
Yes.
And the thought process.
The thought process.
Behind choosing the right tool.
Choosing the right tool for the job.
To the job.
It's all about developing that algorithmic intuition.
Yeah, it's like If you're a carpenter, you don't need to memorize the exact dimensions of every type of wood. But you do need to understand, like, their properties and when to use which wood for a specific task.
That's a great analogy.
It's all about the right tool for the job.
So as we wrap up our deep dive into the majority element problem.
Yeah.
Any final words of wisdom for our listeners who are, eager to put these algorithmic insights into practice?
I'd say, just start experimenting with different approaches.
Yeah.
Even if it's just like small toy examples.
Right.
See how the performance changes as you scale up the input size.
Yeah.
Don't be afraid to make mistakes.
Right.
That's how we learn.
That's how we learn.
That's how we solidify our understanding.
Great advice. It's all about getting our hands dirty.
Get in there.
And seeing these algorithms in action.
Yeah, and remember, there's often multiple valid ways to solve a problem.
Right.
What really matters is understanding the trade-offs and choosing the approach that best fits the specific constraints of your situation.
Well said. I think our listeners are now well equipped to tackle.
Yeah, they're ready.
The majority element problem and beyond. Thanks for joining me on this algorithmic adventure.
It's been a pleasure exploring these algorithms with you.
And to our listeners, keep exploring, keep coding, and keep those algorithmic minds sharp.
Absolutely. See you next time.